Cool. Yeah. So I'm Keegan. Before I get started, I'd like to mention that this is joint work with some fellow ML PhD students at CMU, Valerie Chen and Jun Kim. Their advisor, Amit, and then my advisors, Hoda and Stephen. So, recent regulatory frameworks such as the European Union's General Data Protection Regulation motivate the needs for forms of transparency for algorithmic assessment tools that are suitable for deployment in the real world. So, maybe the most obvious form of transparency would be completely revealing the model that you're using, making it publicly available, and then just letting people see it. However, this can be either like infeasible, intractable, things like that for many different reasons, like privacy reasons, legal reasons, or even like gaming reasons, like Hedia just mentioned. I guess let's revisit this this lending example that Hedia introduced. The setting is you have some banking institution that's making a decision whether or not to give someone a loan, and the strategic agent that wants to get a loan, subject to like some pretty much like effort constraint for not wanting to spend as much effort as possible to get the loan. And you can imagine in a situation like this, it might not be feasible to reveal the model that you're using for, like, say, legal reasons, but you still may want to have some way to incentivize these strategic agents to take, like, quote unquote desirable actions. So in general, we study a setting in which strategic agents can take actions from some like finite set script A. These actions have some effect on their observable features. And then we assume that there's some linear model theta, which is used to make predictions about the strategic agent, which lie in like plus or minus 1. And we just assume that this positive classification is desirable to the strategic agent. And importantly, we assume that this model is not known to the strategic agent. And so the question then becomes, how can we incentivize these agents to take actions which are like more desirable to the decision maker than others? So, for example, a desirable action in this like lending setting would be maybe paying off some pre-existing debt, whereas like how you said, a undesirable action would be like opening up more credit cards. And like I said, if you just recommend like any old action to these agents, there's no guarantee that they'll follow it because they're strategic. So in particular, we assume that they want to get this positive classification subject to whatever cost it takes for them to modify their features for whatever action they chose. And here I'm just like suppressing the y-hat dependence on theta for simplicity. Our goal is to provide an alternative form of explainability in the form of action recommendations. And so we want to incentivize the strategic agent to take actions which are desirable to the decision maker. But most importantly, these agents need to be incentivized to follow our recommendations. Otherwise, they're just sort of like useless. So our interaction protocol is as follows. So we assume that the decision maker and decision subject have some initial prior over what they think the assessment rule will be before it's trained. So the way you can think of this is like some belief about which observable features are important to the outcome being predicted and how important they are. And then so that the decision maker commits to what's called a signaling policy. So I guess what's a signaling policy? So a signaling policy, or I guess what we call it as well, an action recommendation policy, is a mapping from realized assessment rules to actions that the strategic agents can take. And this mapping can be possibly random as well. So they commit to the signaling policy before the model is revealed. So then the model is revealed to the decision maker. So you can think of this as by some training process where you train your model and on some data and you get the model. After which the decision maker recommends an action to the decision subject according to this model or according to their signaling policy. And since I guess we assume these decision subjects are Bayesian, so given this action recommendation according to the signaling policy, they can form a Bayesian posterior update to update their belief over what they think the true assessment rule will be. At which point they can strategically best respond in order to maximize their utility and expectation. So they take a possibly different action or even no action at all. And then they receive a prediction through the assessment rule. Yeah, so I guess now's a good time. Actually, before I stop for clarification questions, now's a good time to mention that so this protocol is between the decision maker and one decision subject. So we can handle cases where there's multiple decision subjects, but I guess I wasn't planning on going into this right now. So yeah, I guess for people that are familiar with the econ literature, this is an instance of a game of what's called Bayesian Persuasion, which is like a popular topic studied in information economics. However, recently it's gained some interest in the computer science community within the last like 5 or 7 years. So there's a lot of work on like bandit problems with incentives, where you have a bandit problem, but you're not the one pulling the arm. These like myopic or strategic agents are the one. Actually, yeah, just myopic agents are the one pulling the arm. And there's also been some work on like characterizing the computational complexity of solving certain like instances of persuasion problems. So yeah, it's like a growing field of interest in computer science. So the question is, how can we calculate the optimal signaling policy for like a given problem instance? An optimal in the sense that you want to incentivize like, I guess, these desirable actions and disincentivize these undesirable actions. So as is the case as with a lot of the literature from Bayesian persuasion, this optimal signaling policy takes the form of a linear program. So basically what this says is you want to pick the signaling policy, so the probability of recommending every action for every like realized assessment rule, in order to maximize the decision maker's expected utility. So we assume they get some utility for each action that the decision subject takes, subject to what's called incentive compatibility constraints. So basically what this says is that for an action that you recommend, it needs to look to the strategic agent that this action is optimal, or at least as optimal as any other action. And the way this is done is by ensuring that the expected utility under their induced posterior for taking this action is at least as high as it would be for any other action. So I guess this is good. We can write it down as a linear program. Maybe what's not so good here is the variables we're optimizing over. There are continuously many of them, because if you're deploying a linear classifier, you need to specify the probability of recommending each action for every possible like linear classifier. So it's continuously many. However, our key observation is that the space of possible linear classifiers can be split into a finite number of what we call equivalence regions, where the number of equivalence regions depends on the number of actions available to the strategic agents. And then basically what we can do is every decision rule which falls in equivalence region, we can treat them as the same. And then we can signal according to which region the optimal, or which region the true model falls into without any loss of generality. So I guess, what is an equivalence region? So first, I guess you need to ask, what does it mean for two assessments to be equivalent? So we say they're equivalent if the difference in decision subject utilities for any two pairs of actions is the same for all pairs of actions. So if this criteria holds for all possible pairs, then we say that these two assessments are equivalent with respect to the decision subject utility. And then an equivalence region is therefore just like the subset of all decision rules which are equivalent. So we can use this to reformulate the linear program. So this is essentially the same linear program as I had written earlier, just written in terms of these regions. So you still want to maximize expected decision maker utility subject to these incentive compatibility constraints. But now the variables you're optimizing over there are finitely many because you just need to specify the probability of recommending a given action for every region. So I guess that's some good news. Maybe a little bit of bad news is that without any assumptions on the structure of the problem, the number of regions, or I guess the decision subjects prior can be exponentially large in the problem size. And this corresponds to an exponential number of regions, equivalence regions, even for simple problem instances, which I guess would therefore make this linear program run in exponential time if you have exponentially many variables you're optimizing over. So even for I guess a setting like this, so an action structure like this might be maybe the simplest or one of the simplest ones you can think of. So basically in this setting you have sort of a root action for doing nothing, and then you have this tree-like structure where basically every single action only affects one observable feature, and each one affects it by different amounts. So even under this rather simplistic setting, there are exponentially many regions, equivalence regions. So some good news is that we can adopt sort of standard sampling-based approximation algorithms to our setting in order to provide polynomial-time approximation. So essentially what this does is if you're given a sampling, or if you're given sampling access to the prior distribution, you can sample from it polynomially many times, and then use that to construct an empirical version of the LP I showed a couple slides ago. And with high probability, this will output a epsilon approximate optimal signaling policy. The bad news is that it only has approximate incentive compatibility guarantees. However, this is due to an information theoretic lower bound we inherit from previous work, which basically says that any sampling-based approximation algorithm cannot guarantee exact incentive compatibility. However, we view an important direction for future work as designing efficient algorithms for priors which can be succinctly representable. So I guess a common sort of observation within these Bayesian persuasion settings is that using persuasion, this decision maker can be or is guaranteed to be no worse off in expectation than if they had not used these persuasion techniques, and they can be arbitrarily better off. And this holds as well in our setting. I'm not going to get into those details, but we wanted to see okay, maybe on average or in practice, where do we fall in the spectrum? Does persuasion not usually help, or does it help by quite a bit? So in order to test this question, we conducted experiments on semi-synthetic data. So what we did was we started with this home equity line of credit data set, which basically consists of data from 9,282 customers who received some home equity line of credit. It consists of 23 observable features and the outcomes, whether or not they repaid their loan. And we adapted this to our setting. And so basically what we did was we averaged over a bunch of different problem configurations where there are different costs associated with taking different actions, and different changes in observable features associated with taking different actions. And we sort of plotted the results here. So we compared the optimal Bayesian incentive compatible signaling policy, which is in red, with two baselines. So one in blue, which is fully revealing the model, which is sort of the common assumption in strategic classification. And the other one is not revealing the model and letting these agents act according to their prior. And on the y-axis, we have expected utility of the decision maker. And so on the x-axis, we plotted three different settings. Basically, this sigma squared corresponds to the amount of uncertainty in the prior. And so, sigma squared is 0.1. There's very low uncertainty. Sigma squared equals 1. There's higher uncertainty. And, generally, you can see that, while this Bayesian incentive compatible signaling policy performs I guess, outperforms these other ones, as it's like theoretically guaranteed to. It gets better as the uncertainty increases, because then you can sort of leverage the strategic agent's uncertainty in order to like incentivize these desirable actions more often. So this is, I guess, a couple slices, a couple instances. So you can see here we vary on the x-axis, or yeah, on the x-axis, the change in one observable feature for taking one action, and on the y-axis we vary like the cost of taking that action. And then the z-axis we plot the utility. So this is like some like manifold, and the red manifold corresponds to our optimal Bayesian system compatible signaling policy. The blue and green ones correspond to the two baselines. You can see that it outperforms these. So maybe just to recap, we show that in the setting we consider, the decision maker can leverage their information advantage about this model in order to incentivize these strategic agents to take desirable actions without revealing the model to them. And like I said, the decision maker is never worse off in expectation, and they can be arbitrarily better off depending on the problem instance. We can essentially reduce this problem to signaling based on which equivalence region the true decision rule falls into. And then, therefore we can solve the problem using a linear program, which may be exponentially large. However, we provide a computationally efficient approximation algorithm, which provides an approximate solution in polynomial-time with high probability. And then finally, we empirically evaluate our results with semi-synthetic data. So yeah, thanks for your time.